Yeah, so my name is Matti Laakso. I work for KONE Corporation and for the R&D of KONE Corporation. So our R&D is divided in two parts. There's the equipment R&D, who design new elevators, new escalators, and components for those devices. And then there's the services and solutions R&D, where I'm from. And we are doing R&D on new services like digital services and related solutions. And also we are doing maintenance development. So predictive maintenance and digital services combined. This is something that is for the services and solutions R&D. So KONE is one of the largest companies in Finland. So I think we are the fourth largest provider of elevators and escalators in the world, and our customers range from small, let's say, housing cooperatives who might have just one elevator in their apartment building, all the way to very big customers that have, let's say, that run an airport or even multiple airports, shopping malls, and so on. So the criticality of the equipment of our customers there's a large variation. So of course the let's say it's very important that an escalator at a big shopping mall, let's say in terms of money, that it keeps running continuously, whereas it might be more acceptable for some elevator that is less used to suffer a short amount of downtime. In addition to providing this new equipment to new buildings, we also modernize old elevators and old escalators. There are many kinds of modernization packages available, and then we maintain all of our own equipment, also all of our competitors' equipment. So we are not restricted to just KONE devices. We have 55,000 employees. For example, almost all of the field technicians that are maintaining our equipment are actual KONE employees. Net sales was 9 billion euros last year. Out of that, about one half is or a little bit less than one half is from new equipment business, and then the other half is divided. Let's say about 30% of our revenue comes from elevator and escalator maintenance. So we have about 1.2 million elevators and escalators in our maintenance. There's I think a little bit less than 1 million of those are elevators, the rest are escalators. Then we also have building doors, so these automated doors and some access control solutions that we also maintain. So like I mentioned, in addition to maintaining our own devices, we also maintain our competitors' equipment. So whatever the customer has, we perform maintenance on those devices. And let's say of this 1.2 million, or if we take the elevators, so I'm from the elevator side, so if you take the 900,000 elevators or so, about 1/3 of those are KONE equipment, and the rest is either our competitors' equipment or some really old devices that might have been acquired by KONE or that might have gone out of business. So beginning of last year, we launched our new service offering, which is called KONE 24/7 Connected Services. Our marketing campaign included talking elevators, and now beginning of this year, we enlarged this, or we also started to offer this 24 connected services to devices, to equipment that is not made by us. So this third party equipment, and also the old elevators and also the escalators are now under this 24/7 connected services. And this 24/7 connected services it's a unique offering in the elevator and escalator industry. So it's a fully it's a service based on real-time data that is coming from the equipment, and the analytics that is performed on this data. And of course, what we aim to do is to keep the equipment running, the availability of the equipment as high as possible. So that's the goal of the predictive maintenance. I can tell here that at first we planned that, okay, this is also a way to increase the effectiveness of our maintenance technicians, so that we might be able to let's say, visit the equipment less often. But there we have found out that there are actually, I mean, the contracts that we have, there's also a lot of local regulations that dictate how many times we have to visit, let's say, an elevator per year. So it could be 4 times per year, completely regardless of how much it is used. Actually, in China, we have to visit elevators 26 times per year, so every 2 weeks, just to do some basic checks. These are mandated by the government. But as we launched this service and started getting data, we found out that actually there's a lot more that we can do with the data. So we can also offer new services to the customers, and this way also get extra revenue from the data that we are gathering from our equipment. So in this presentation, I will dive a little bit deeper onto what makes this 24/7 connected services tick. So what kind of solutions do we have under the hood, and where we are right now in this predictive maintenance of elevators. So the challenge is that before I joined KONE, let's say about 4 years ago, I thought that elevators are pretty boring. They just move up and down. But it has turned out also to me that elevators are not just a bunch of homogeneous boxes that are moving up and down. So there might be some elevator which is 100 years old, traveling at let's say 0.5 meter per second and serving 3 floors, so let's say 10-meter hoisting length. That's on the one end of the spectrum. The other end of the spectrum might be one of our latest and greatest modern elevator, traveling more than 10 meters per second, where the hoisting ropes are made from carbon fiber composite materials, and which might have a hoisting length of let's say even 600 meters. So there's really a large variety of elevators, and this makes it challenging to offer predictive maintenance to all kinds of elevators. So our own equipment, we've been gathering data ever since we launched our, let's say, modern KONE electrification. This was about in the beginning of about 2000, I think 3 or so. So almost so about 15 years we've been having a remote monitoring of our own equipment. We didn't call it Internet of Things back then. We just called it remote monitoring. We used analog phone lines to transmit data basically once per day. And this includes usage statistics and fault codes. So just like all of, or those of you who have relatively modern cars, let's say from the last 20 years or so, the cars have onboard diagnostics. They generate fault codes. Elevators, it's pretty much the same. So when there's the modern electrification system, it's able to monitor itself and generate fault codes based on conditions that are somehow abnormal. And we've been gathering this data ever since we've had these remotely monitored elevators. We've also, of course, from our own equipment, we've been able to gather complete service history. So we've gathered all of that data, the spare parts consumption. So whenever there's been parts that have been changed, we get that all logged. And also in the recent times, we have full bill of materials in digital form for all of our new deliveries of elevators. So with these fault codes, we've actually been able to do this predictive maintenance already for some time. Usually fault code means that there's already a problem with the elevator, but many of the fault codes might be intermittent in the sense that they come and go, and if we monitor these closely enough, we are able to predict that, okay, something might happen in the near future. So that's something that we've been doing already for a long time for our own equipment. But now, like I said, from the beginning of this year, we have started to offer this also to all elevator types and models. So majority of our service base is something else. About 30% is this modern KONE equipment. The rest, 60-70%, is our competitors' products, old KONE equipment, or some other really old equipment. And how we do predictive maintenance for those is that we take a set of sensors and retrofit the elevator with those sensors. Of course, our competitors' devices, they also have modern control systems which provide fault codes. Unfortunately, the interfaces are usually proprietary, locked, and therefore difficult for us to use. So we have decided to go down the route of retrofitting sensors to the elevators. Some basic set that can be installed quickly to any elevator and at a relatively low cost. One problem with this equipment that has, let's say, come from a service of some other company, our competitors, or some old equipment, is that we might have unknown service history, and we might not know even what kind of parts the elevator has in it. So for that, we have to also rely on the back reporting from our field technicians. So whenever they go on site, perform maintenance or some checks to an elevator, we always get a back reporting, and we get that into our data platform, basically what has been done to the elevator, what kind of parts have been used, and so on. Okay, so if we go into the let's say, compare elevators to some more traditional machines, I've taken an example of an escalator here as a traditional machine. An escalator is something that runs constantly. Okay, during the night it usually is stopped, but during the daytime it runs pretty much all the time. Elevators, on the other hand, they have usage patterns that vary a lot with time, with weekdays, holidays, and so on. So there's a lot of randomness in elevator motion. Also, the ride durations maybe are very different. Whenever the elevator moves, it can move 1 floor up, 2 floors up, 7 floors down, and so on. So there's a lot of variety there. Escalators move with constant speed, or there could be 2 different speeds, let's say full speed and a low power mode. And they move in one direction only. So typically there's a dedicated escalator for upwards movement and downwards movement. Elevators, on the other hand, they move with varying speeds. So it might be that the elevator doesn't have time to accelerate to full speed, and it can move up and down. So there's a difference there. Escalators, they have varying load depending on the number of people that are traveling with it. The same is true of an elevator. There can be, elevator is also quite often moving empty when it's serving a landing call, or it could have a load of, I don't know, let's say 10 passengers or so. So all this makes the consistency of an escalator makes it a pretty easy target to model. So you can just, let's say, take an autoregressive integrated moving average model or some supervised learning algorithm like support vector machine, model the elevator and start looking for deviations from the model, react on those. Elevators, on the other hand, they are a lot more difficult to model. So I have colleagues who are doing predictive maintenance of escalators, and those guys sure have it easy. It's a lot more difficult for us. So why is it so hard to model an elevator? So in the previous slide, there were some differences that already are one reason for this. But another reason is that the elevators are very much unique. So we have a huge variety of brands and models. If we have a modernized equipment, it can have, let's say, the motor can be changed separately from the rest of the parts. The frequency converter, doors, signalization, meaning the buttons and the displays and so on. Those all can be changed, and they could be from different manufacturers. So we can have a real like Frankenstein monster type elevators out there that have been modernized maybe multiple times. And even if we have 2, let's say, identical elevators, they might have completely different operating environments. One could be in Saudi Arabia in a, I don't know, temperature of 40 degrees Celsius. The other one could be here in Sweden, taking people from underground parking garage to a street level where there could be minus 20 degrees Celsius outside. There could be different shaft lengths, so anything from few meters to hundreds of meters. And there's a lot of configuration parameters in the elevator electrification that can be tuned to make the elevator behave differently, even though the models are pretty much should be identical. Another problem for modeling elevators is that they are in general very reliable. So if we, let's say, we want to have some classification data for an elevator failure, it's pretty difficult to obtain that because the failures just happen quite rarely. And even if we instrument a large amount of elevators for a sufficiently long time to really collect information where there's elevator failure, it turns out that also the failures can be pretty unique. So one failure might only happen, one type of failure might only happen once. So that's really bad for, I mean, in terms of statistics, we have really low amount of data for a failing elevator. So we get a huge imbalance in class size. It could be that we have 1,000 times more data on a well-working elevator compared to a failing elevator where there's something wrong. Okay, so of course one could use unsupervised models to get around this problem of let's say use these anomaly detection methods that have been discussed already today. But even there are a few problems. So here's one example, just an acceleration curve of an elevator in 3 different models. So here the elevator is moving up, it accelerates, drives at constant speed, and decelerates. The first one here is an example of an old elevator where the elevator motor just is turned on and then off when it's let's say close to the destination, and then there's a mechanical brake which actually stops the elevator. And this usually ends or causes a pretty abrupt elevator motion, so it's jerky, and also the one problem is that the elevator might not level correctly because it's mechanical brakes that stop it, so it could be plus minus 2 centimeters from the floor, which creates this annoying gap and could cause people to trip on when exiting the elevator. A little bit newer elevators might have 2-speed drives, so there are 2 motor windings for 2 different speeds, and there the deceleration part is done in two phases. First, the elevator drops to a lower speed, and then the final deceleration to the destination is done with the mechanical brakes. The latest elevators have variable frequency drives in them, and there the acceleration and deceleration are smooth because the elevator motor speed can be varied continuously. And there we also have a closed loop control so that the elevator also stops exactly at the landing. So these are traction elevators, so meaning that there's these hoisting ropes and there's the counterweight, so the elevator is pulled with the ropes. There's a 4th type of elevator that is even more difficult to model. There's the hydraulic elevators. They behave a lot differently. There, even the hydraulic oil temperature will cause differences in the elevator behavior because well, the elevator is pushed up by pumping hydraulic oil into the pistons, and then when it's moving down, the oil is let out of the pistons, and then the viscosity of the oil causes large differences in the elevator behavior, how it accelerates and decelerates. So if we, let's say, take this acceleration, the height of this acceleration peak, for example, that could be one thing that we might want to monitor. It's pretty similar in all these 3 cases. But then, let's say, if we travel different distances in the shaft, of course, this constant speed phase will get shorter as we drive a shorter distance. But then, if we travel, for example, just 1 floor up, or even a half a floor up, then as this length here goes to 0, then the acceleration and deceleration peaks start getting smaller. So depending on the length of the elevator drive, the acceleration peak can look a lot different. And then if we want to use, for example, anomaly detection methods for this height of the acceleration peak, the distribution of these numbers might look something like this. So it's not a normal distribution at all. And then when we actually group by the traveled length of the travel length, then do we see that okay, it's actually composed of 3 normal distributions, and then if we start to look at these individual distributions grouped by the travel length, then we might be able to start seeing anomalies in the data. Okay, so that was just one example. This height of the acceleration peak. We could normalize the peak height over travels of this single individual elevator, like there. So grouping by the travel lengths and getting 3 different distributions. And then we could start comparing to the historical behavior of the elevator. But for example, if we have an elevator that has been maintained by some other company, we might not know exactly that what is normal for that elevator. So another way that we could do it is we could group elevators by type and then start normalizing against some reference group. So let's take single speed elevators from a certain brand, certain model, and normalize the acceleration peaks in that group, and then start seeing differences among different elevator individuals. Or if we want to have, let's say, some general model of a general elevator, we might take all of our elevators in our service space and try to somehow normalize for example, this acceleration peak height across those. So these are the kind of things that we have to struggle with to be able to do predictive maintenance. So so what we actually do is let's say to get this peak height of the acceleration peak height. First, we have to find out that when is the elevator in a certain interesting state. So we want to divide the elevator travel to acceleration phase, constant speed phase, and the deceleration phase. That's the first part. Then we extract some features based on this segmentation of the ride, like I showed before. So we might take, for example, the acceleration peak height, and then do some statistical testing to determine whether this is normal behavior or not. But there are actually still multiple variables that we have no control over, that we are not able to monitor. So for example, the number of passengers in the elevator car is something that will definitely affect the motor load, and from there it affects the acceleration and deceleration of the elevator. So even if we do this normalization over the travel lengths, there is still the unknown number of people inside the elevator. So we are not able to just take let's say traditional statistical tests and say that okay, this is now an abnormal ride. Instead, what we do is that we generate events that on their own might not signify anything like a failure in the elevator, but then we can use those kind of like fault codes in our own modern equipment, that we collect a time series of these events and start looking at patterns in these time series, and those we can use to actually determine if the elevator is failing or not. So we create a feature vector out of these events, and those we can then feed to machine learning models, for example, to generate alerts, and then really send field technicians out there on the field to check the elevator, what is wrong with it. And here, like discussed in some earlier presentations, an important thing is that we close the loop. So once the technician has visited the elevator to determine that okay, it's okay, now the problem has been fixed, we want to know that what did he do, and if the alert that we generated, if it was meaningful. So to close the loop, we can improve our models. So in this presentation, I described, let's say I took the acceleration as one number that is interesting in the elevator hoisting movement. Unfortunately, the real problem that we have with the elevators is the doors. So they are the user interface of the elevator, in addition to the buttons inside the elevator car. And the doors are the parts in the elevator which fail most often. So there can be just something really small, like a pebble in the door sill groove that causes the elevator door to stop before it's able to close properly and do these repeated reopenings. And with the doors, we have a similar problem or similar challenge as with the elevators, that we have a huge variety of different kinds of car doors, different kinds of landing doors. Even a single building might have different doors on different floors. So there we have even more variety. But also there, the solutions are pretty similar. We can extract some common features out of the door movement and generate events, and then take this time series of events and use that to do predictive maintenance. So then we can also catch the elevator failures caused by door problems. Okay, so to wrap it up, something that I might like you to take home with you is that that in this kind of predictive maintenance for elevators, the crucial step is to first extract useful features out of the sensor data, and then if your let's say service space is wildly different, then this intermediate event generation is an important step to be able to really use machine learning models. And something also that has been said already multiple times today, it's very important for the data scientists to have domain-specific knowledge. So the data scientist needs to know what kind of data he or she is looking at to be able to really create the models, create meaningful models. Okay, thank you. And,